This is the limit definition of the derivative. Well, one of them. If someone threw a brick at your head as a kid, then maybe the others are useful. We will start by applying this formula to three classes of functions: polynomials, trigonometrics, and exponentials. Kind of. The former requires the binomial theorem, so I hope you still remember that. We'll start with single-term functions that have coefficients of 1 first. We know how to substitute f of x, expand, and simplify to this form. Now, h is not 0, it's only approaching 0, and therefore we can cancel these h terms over here. We're left with this batch of sums, and because there aren't any indeterminate forms here, we can use direct substitution and the zero product property to eliminate all of these terms, which are as many as you'd like. If you're wondering why h can be treated as 0 here but not earlier, I'll refer to the same explanation in the description, because it's more than likely that your math test won't care about it nearly as much as you do. For polynomials, we can use our first function operation rule, the sum rule. The derivative of a plus b is equal to the derivative of a plus the derivative of b, given that those latter two things actually exist, of course. This is because the derivative is just a limit, and this rule is true for limits as well, as we've seen already. Take this example. Split the sum and then apply the monomial process, known as the power rule, to each term. This technique is so consistent that my math teacher allowed us to do it all in one line. Next up are the trig functions. Before we do these, we're going to have to prove this limit. Even though both the numerator and denominator are continuous, evaluating directly gives 0 divided by 0, so that won't cut it. Instead, we must use something called the squeeze theorem, which basically states that if these two statements are true, then so is this one. In practical terms, it means that if one value is always between two values which converge, then the value in the middle point must be in that smaller and smaller range, anywhere near the point of convergence. Now let's get back to solving our limit. If we take a look at this diagram, we can see that the area of the blue triangle is always greater than that of the white sector, which is in turn always greater than the area of the yellow triangle. Using basic area formulas, we can compute this statement as an inequality and then manipulate it so that our initial expression is in the middle. This is true anywhere within this range, which includes 0, so it satisfies our second condition. Next, we can evaluate the limits of the bounds, which satisfy the first condition. Thus, the limit of sine x divided by x as x goes to 0 is 1. Now, if we try to plug the sine function into the derivative definition, we can use an angle addition identity or two, resolve these limits, and we're done. We can do the same thing to find the cosine derivative, and for the rest of them we're going to need to back up a little bit. We have to handle these reciprocals somehow, and for that we're going to need the quotient rule, which means we need the chain rule. I will not prove the chain rule because I'm too stupid to understand it. Anyways, this quotient is the product. Oh fuck, we gotta go back again. The product rule can be derived by cheating your way into factoring by grouping, akin to the sum to product rule, and then direct substitution because everything is continuous. A function's reciprocal can be thought of as the composition of that function and the reciprocal function. Use the chain rule to get the derivative of the denominator, and then the product rule to get the derivative for the whole thing. Now we can apply these rules to the rest of the trig functions, and I've added some color coding so you can follow along a bit easier. Lastly for now are the exponentials, which we're not going to do because I'm sick of the squeeze theorem already. Instead, let's plug the natural logarithm into the derivative definition, since we can use the logarithmic properties to reduce it instead, and then the chain rule since we know what the composition of the logarithm and exponential are. Alright, first use the addition rule to merge these two terms, then the exponent rule to remove the denominator. Now we have an expression inside this logarithm that looks eerily similar to, and by that I mean exactly the same as this definition of the constant e. We can now move on to manipulating this limit. Because x is not 0, h of x will always approach 0 as h itself approaches 0, so we can simply swap them out. Simplify this exponent, use the definition of e outlined earlier, cancel some shit, and arrive at our answer. The range of the exponential is the same as the domain of the logarithm, so this will always be true. For the exponential derivative, use the chain rule and isolate the stuff. This is a really snooze-worthy answer to why e to the x is its own derivative, as it should be. Now we can put all this together and finally derivatize this thing. Before we begin, however, I must revisit the power rule for a bit as I promised, as well as the chain rule, which can actually be generalized to an unlimited number of compositions. Imagine the composition of an arbitrary number n of derivatizable functions, which are labeled f sub 1 to f sub n. We can define this next set of functions with this recursive rule and express this in terms of the two-function chain rule. Next, we derivatize. This produces another derivative, which we can simplify again using the recursive rule earlier, all the way down. We can also back substitute to simplify even further. Here we go. On the bottom right, we have a key that will show us what kinds of function operations or derivatives to take. We start off here with the product, so naturally we use the product rule to split it. Next up, we have a lot of things. This composed logarithm and this polynomial. So we use the chain rule, logarithmic derivative, and power rule respectively. Now we have this product, but we'll use the quotient rule as a shortcut. These endmost derivatives are the sine and some monomial, so their computation is trivial. Simplify some stuff, and we're done. Realistically, however, you probably have like another 20 of these to do, so good luck, unless you don't need it.